All right, so for your pre-lecture, you guys were introduced to the energetic principle behind chemical bonding, as well as the beginning characteristics and naming rules for ionic bonds. So for your do now, you guys were asked to, I'm just gonna zoom in. You guys were asked to describe the 4 stages of bonding using this potential energy internuclear axis kind of, or radius graph. This is a very common graph that they give you on the AP where you have to interpret it or make a decision, or you have to identify an element based on its graph compared to another element's graph or diatomic elements graph or something like that. Usually a binary compound, a two atom compound is what they look at, right? Because it's just describing 2 atoms coming together. What was the first stage? Yes, Maggie. Maggie, would you like to explain the whole thing for this? Let's see, this type of graph.
So at stage 1, the atoms are separated, right?
Okay, stage 1, atoms are separated.
And then stage 2, there's like an attractive force pulling it all in.
Okay.
So the distance is decreasing.
What is that attractive force? Also, where'd Kevin go?
Just an attractive force. Loki, don't remember.
Okay.
An attractive force.
Think Coulombic attraction, it's 2 nuclei, so it's the mitosis. No, it's the each nucleus pulling in the respective electrons of the other atom. Okay. Then step 3, stage 3. Max stability, which also includes what? What other things how else can we identify max stability? Octet, what else? Not for everybody, but for most. Sure, that's what an octet means. What else? Yes, what else?
Ideal bond length.
The potential energy is at its lowest state. Because when we think about energy, okay, think about potential energy is based on position, right? Up here, I'm very unstable. Wiggle, wiggle, right? I have a lot of ability to turn into kinetic energy to fall. There's a lot of instability with this position, right? But when I'm at a low state, at the ground state, not for some of you just like trip standing, but like most of you are more stable at a lower ground state, okay? So, you're welcome, future classes. Good. So bond length. There's an ideal bond length. There's an ideal distance between the 2 atoms in a bond. Okay. Then what happens stage 4, Maggie?
The distance is too great, and it.
Too great?
No, too small. Sorry, they're all too close together.
Yeah.
It doesn't work out very well.
It's claustrophobic for those atoms. Those nuclei begin to really reject each other. Like, you know how you can like be stuck in a room with someone that you kind of don't like? That might be me. Okay. And you're like, if I keep this amount of distance, this is about as close as I can get. Right? That's as close as I can get. But if you get any closer, you start like, revolting it, right? A little bit vibe. Okay. That's the same idea. Okay. Push somebody too close and they don't like it. Right? So good. Okay, that's a good warm-up for the do now. You should know how to interpret these potential energy internuclear distance diagrams related to specifically the bonding patterns between 2 atoms. All right, because you're going to learn about another potential energy diagram, totally different. Okay, second one. What are some of the characteristics of ionic bonding? What are some of the characteristics of ionic bonding? They don't share. What do they do, Malcolm? They generally form between metals and non-metals. Also, Hannah, I do not know when my convenience is, but I guess my convenience is your convenience. They generally form between non-metals and metals. Okay, what else do we know? Evan. They always take on a charge because it involves what? Full transfer of electrons. If I have a full transfer of a particle, that means I've lost a full charge because an electron is a -1 charge, or a 1- if I want to say it technically correct, a 1- charge. Welcome back. A 1- charge, okay? So if I fully transfer electron, I'm losing a full charge, okay? It's kind of like a dollar bill. When you lose a dollar bill, you don't rip it up in half and you're like, oh, I'll keep some of it. No, it's like, it's gone. It is gone from your account. It is no longer yours. You made that transaction with the hope that it'll bring something better. Hope, right? Don't fall for those Instagram scams. All right, he made it. He made it out the door. So what else do we know about ionic compounds? What are some other terminology you guys learned? What are some other ways to know that you built a good one, Nora? Yes. How do you know you built a good ionic compound? An ionic bonding based compound? A good ionic based combination? You know, because the charges cancel out to zero. It indicates something. It indicates that everybody got their octet or maybe a duet. It indicates that everybody got what they wanted out of the transaction of the electrons. And it is a transaction. It is a full transaction. That really does matter. What else do we know about them? Well, how about naming rules? You're literally looking at some of the naming rules right now on the screen. We got a lot to get through today, guys. Start saying something. Yes, Annalise. It's great. The anion is the negative charge. The cation is the positive charge. You always want the cation first. And by the way, we have to change the last syllable of the last element because otherwise it just sounds like you're listing two atoms together that are just like there. And you're like, okay, it's kind of like when you put a last name. It's like if I just say Maggie and Allison, because that's my name. Okay, if I just say, you're not allowed to call me that, by the way, Maggie and Allison, okay, it just sounds like two names. Now, if I say, let's pretend that we're siblings, I'm obviously the adopted one, okay? If I say Maggie and Allison Gallup, Maggie Gallup, Allison Gallup, now you know that we're connected, right? That's what IDE does. Okay, that's what IDE does. It's like, I'd love to be in a bond with you. Okay, it says to that person listening, oh, hey, this isn't just calcium and oxygen. No. This is calcium and oxygen bonded together through the full transfer of electrons through an exchange where my sum of the charge is equal to zero, indicating to me that I did it well, right? It's kind of like the idea of debit and credits. You should have the same amount that you lose gained by the other person. If you lose 20 and they only earn 15, somebody is embezzling money and that's illegal and you go to jail. Okay, so you need to have a consistent exchange, right? Don't go to jail yet. Just kidding. Don't go to jail.
No, actually, go to jail now.
Okay. You know, the legal system is a little kinder to you, but I still wouldn't do it. It doesn't look good on job resumes. Not like I would know, but okay. What else do we got? Okay, name the ionic formula or wait, name the compound or write the ionic formula for the following. TiG Willikers. TiO3. What was the name for this? Was that, I can't read my own handwriting. Is that a CO? Hey. I'm at a weird angle. Let's, whoa. Okay. Where's Keaton when I need his whoa? Okay, what do we have? What's the name of this? Titanium chloride, is that it? Are we sure about that? Yes, Jaden? No, but that's okay. Think about it. What is titanium? What's so unique about titanium, that metal? There's a really unique category, Malcolm. It's a transition metal. Does someone want to modify their name? Knowing that titanium's a transition metal. Liam?
Titanium 3 chloride.
Titanium 3 chloride. Titanium 3 chloride. Why? Because a transition metal is multivalent. It can take on many charges. There's no set amount because it's not really part of the S&P orbital. Notice the titanium valence electrons fall in the D and F, right? Or it's part of those weird transition metals, the inner transition metals and the general transition metals. It gets funkadunk. Okay, that's what the F orbital stands for funkadunk. I also say the don't F with it orbital because that's where the nuclear stuff is. But oh, parents watching this. Titanium 3, you have to signify the charge based off of the Roman numerals. Otherwise, you'd never know. I could say titanium chloride and it could be titanium 2. It could be titanium 1. It could be titanium 5, 6, 7. You usually don't go past that. But okay, that's why it matters. Okay, next one. Now I give you the chemical name. Give me the formula. It's lithium sulfide. Lithium sulfide. What do we got? Li2s. S2, because we use subscripts to represent the ratio between the atoms in a bond. The big numbers will come into place in a little bit. The big number will come into place in a little bit, but not yet. Also, peanut gallery in the back, your vocals are coming through, so be careful. Okay. So, do you guys know what the peanut gallery is? And like, it's just to reference the baseball term. Okay, somebody asked me that recently. I was like, oh my, yeah. So anyway, all the parents listening to this who are unfortunate enough to hear this in the background of your home, I have old parents, so I feel you. Okay, not to say you're old. Not to say that you're old. My parents are probably definitely older than all your parents. Yeah, they're boomers.
If it was 2 sulfurs and 1 lithium, the charge doesn't the charge have to be equal? So
Oh, you're saying lithium 2 sulfur. Oh, yeah, we wrote that wrong, folks. Lithium 2 sulfur, sulfide. That's what you were trying to say. I thought you meant big 2 in front of the
I was
S.
saying 2 lithium.
Hayden's right. Hayden's right. Maybe Hayden, maybe you'll be my new Keaton where I like look at the answer key and think it's wrong and you're right. Lithium 2 sulfide. Thank you. Do we need another Keaton? We always could use more Keatons in the world. I need more Keatons in my life. I don't know. I don't know where Keaton is. So Keaton's my hero. So although Charlie's becoming my new Keaton. What a hero. Okay, so lithium sulfide. Good. Okay. How's everyone feeling? You have a ton of workbook problems. Honestly, here's the thing. You will never be asked explicitly to do this on the AP exam. You will be given a problem where you're given a formula or you're given the name of it, and you have to know how to do it. Like, it's never going to be like a point problem. It's going to be part of a problem. They just assume that you know how to do this, by the way. So if you're one of those people that's like, I don't need conceptual work, just humor yourself. Humor yourself. Do a few practice problems that are conceptual on naming. It will, because I'm about to introduce another type of bonding, and the naming seems very familiar, but it's not. Okay, so good. All right, let's get out your notes. Let's continue on to our journey of new material. So I've introduced single element ions. Single element ions. I'm going to introduce a new one that's actually a molecule in itself that acts like an ion. These are called polyatomic ions. And these ions, okay, are a group of, oh goodness, covalently bonded atoms that together carry a charge. Okay, that word covalently bonded is going to matter, okay, because that's a different type of bonding structure. So it's actually a bonding within a bonding to act like one type of bond. Yes. Guy, did you have a question? Or are you just raising your wrist? No, it's okay. My wrist also flaps. Don't worry about it. Okay, so it's a group of covalently bonded atoms that together carry charge. You can kind of think of it like a soccer team, or like when you guys get together, like when I get together with my girlfriends, we're gonna have Valentine's Day. Yeah, we're gonna have Valentine's Day and Valentine's night. When we get together, we all become different people. Okay. What happens when you get together with a team, a group, you function as a different kind of one unit. Okay. We all giggle and gaggle and laugh and do all that stuff. Okay. Which I actually kind of do already, but it's different. Okay. Same thing here. These atoms alone would be actually under a different category of bonding, but because they carry a charge, they can now engage and act like something else, an ion, together as a whole. Not the individual atom itself, but the group of them together act as an ion. So if you have multiple polyatomic ions in a compound, such as this, okay, you put parentheses around the group because, of course, if you wrote it like this, SO32, that becomes a non-existent molecule of 1 sulfur connected to 32 oxygens. So we don't do that. That's crazy. That's crazy. So what we do is we're smart about it and we section it off and say this unit, I have 2 of those units. Okay. Now sulfite is a polyatomic and it has a charge of 2 minus. So this would be telling me I have 2 sulfite units with a charge of 2 minus. So that means that, by the way, my cation must have a charge of what? If I needed 2 of them. Must have a charge of, Annalise? 4+. Excellent. That whole table you need to memorize. This is all you, boo. Get out your Quizlet. Get out your flashcards. Get out your little handy. Get out your friends who can help, who are like English people right now, who are just chilling McMillan. Okay. Call them up on the Zoom, the Discord, or whatever you guys do, video chat life. Okay. And do that. There are more, such as this one really common right here. Here are some of the most common: acetate, phosphate, hydrogen phosphate. All the phosphates are pretty common. Sulfate, sulfite, nitrate. You know what? Actually, you know what they are all really common. There's another one that isn't written on here that I highly recommend that you look up. Oxalate. Oxalate is a really common one on the AP that might just be helpful to identify that that is a polyatomic. Okay. So just like a key little thing right there. All right, and I realized I kept it in the same highlighting color as the covalent, so I won't do that. Okay, so moving on. Okay, so when we name with polyatomics, it's pretty much the same rules except for this. You don't need the "-ide" anymore, unless your polyatomic is the cation, because the name itself tells me it's a polyatomic. It's kind of like saying, like, hey, I'm Edward IV of England, okay? I don't need to add the England if you're the only Edward in England, right? Like, obviously, okay? So the polyatomic name itself, we just keep, okay? So why don't you try, I'll do one. The first one will be calcium, okay? Carbonate, not carbonide, carbonate. It's just the name of the polyatomic. We still keep the rules though of cation first, anion second. And we still keep the rules that we do not put in the number of each ion because we assume you can do math. A calcium is a 2+ charge. Carbonate as a whole is a 2- charge. So we're in a 1-to-1 ratio anyway, but even if we needed 2 of them, we would never say calcium dicarbonate. Like, no. We assume you can do math. We assume that you memorized all of these polyatomics. Try the next 2 on your own. So what you should have gotten was, Nathan? Sulfite? Sulfate, everybody. Aluminum has a charge of 3+. That's a set charge. That's a charge based off its position on the periodic table. That missed my, thank you. Okay. Sulfate has a 2-. So what do you got to do? You got to find the common multiple, and that common multiple multiplier becomes a subscript. Right? Because you got to get the charges to cancel. Next one, Sachin. Hold it. Lithium sulfide. Please do not mix up your ites and your 8s. They're different. Okay. So practice problem. We don't need to do this very in-depthly. I think we're good to move on. So I'm going to move on. So there's a special naming. Sorry, guys. We got to keep pushing. It's part of the deal with spring. I deeply apologize. So you guys can do this on your own in like 3 seconds when I get distracted again. So oxyanions are a special category of polyatomic ions with, okay, oxygen. Okay, oxyanions, oxygens. So by the way, where did we get the ite versus the 8? You should notice something that the larger or the greater amount of oxygens present in the polyatomic, you get to 8. And then you add a per 8 if you have a lot of oxygens. Notice sulfate is a 4 oxygen. Sulfite is a 3 oxygen. Okay. Same combo of elements, different amounts of oxygen. So you'll see that this is a pattern. It just helps you. It's a pattern. Honestly, if you're like, I can't memorize this, just memorize the names of the polyatomics and forget about this. But you should know that there is actually like a rhyme and a reason to it. So how about when you have a hydrogen containing one? So you'll see that this is an old school way of naming. Hydrogen phosphate, dihydrogen phosphate, a hydrogen containing polyatomic. There's another way that we name. We add a bi in front of it. Okay. So what we say is that instead of saying hydrogen carbonate, it's bicarbonate. Instead of saying hydrogen sulfite, it's bisulfite. You could also say hydrogen dihydrogen. There are about 5 to 6 different naming systems in chemistry. You are learning not the professional one. You are learning the most basic one. When you get into higher level chem, it's called IUPAC naming system. That's a doozy. That whole name is where you get those massively long chemical names that have all those dashes and numbers and weird things that you've never seen before, primes for one compound. That's the IUPAC naming system. We are not teaching you that. You're welcome. Okay. So when we look at ionic compounds, let's take a moment to see what they're like as a salt. Okay. They build specific structures. And by the way, any ionic compound solid is literally called a salt. So when you look at NaCl, you basically name salt after its generic feature, but you're basically just calling salt an ionic compound that's a solid. That's actually the translation of
We
salt.
named it salt because it looks like salt.
No, we named it salt because it is a salt,
Oh.
but not because the actual elements inherently make it salt. Yeah. Okay. So what we see is that we see it basically create a lattice structure. Okay. We say that we have, okay, a lattice structure. Sorry, I went on to the next page. It's a series of repeating units, okay, held together by electrostatic forces and by electrostatic, I mean the positive / negative force, right, of your cation plus your anion. So basically what you see is for this lattice structure, it's like one giant ionic compound. Your positives are arranged around your negative, like a tic-tac-toe, and your negative is arranged around your positive. They're very strong because everything is what we call an intramolecular bond. It's a bond-based structure. Yes. Why are you making that face?
I was making a face.
Oh, it's just your face. Okay.
That is my face.
Okay. So what we say is that in these ionic compound lattice structures, we maximize attractive forces and we minimize repulsive forces. So that's why we arrange it positive to negative and not positive to positive or negative to negative. Notice every pink is next to a blue. Every blue is next to a pink. Okay. Just think about it as your 3D tic-tac-toe. Okay. You are unable to conduct electricity in a lattice structure. This will become important in a second when we talk later about ion formation. Lattice structures, solid forms of ionic compounds are just cubes. They don't do anything. When you break them apart in water, magic happens, which is, by the way, why you get electrocuted in chlorinated water. Okay, so that matters. It takes on a different property. So, right, but I'm never in the pool because I hate swimming. So, there's also another unique thing that you've already started to encounter. It's called a hydrate. A hydrate is an ionic lattice structure that has water molecules trapped up in here in the little in-betweens. Okay, that's, what's that thing up in here? Was it like a song or something? So an hydrate is an ionic compound, an ionic lattice structure, solid, okay, that has water molecules trapped inside. But it's still technically a solid. Like it's not enough water molecules to like liquefy it. All right. So we call it a hydrate. Now, you guys already worked on this on your test. There is a molar ratio between every unit of ionic compound to hydrate present. We use Greek prefixes to represent that. All right. We use, if there's a 1 to 6 molar ratio of ionic compound to hydrate, we say something, something ionic compound, hexahydrate, 6 water molecules trapped inside that. All right. Sorry, I have a really bad habit of looking mainly to the right. So I'll try to remember. Yeah, I'll be better about that. Your all faces are beautiful, so I don't want to ignore them. So calcium, okay, calcium chloride monohydrate would be written like this as a chemical formula. Big dot H2O. That big dot tells me that there is a dot of water trapped inside that lattice structure. That's how you can remember it. That big dot is that water molecule trapped inside. Okay, this one would be copper or cupric. Copper also likes to go by the term cupric. It's equivalent. Copper Okay, copper is a transition metal. So copper 2 sulfate. Okay, and then what we call it is pentahydrate. And you do not need to put the enter in. It's just that I ran out of room. Pentahydrate. Yes.
How do you know what the one you want to do?
Because sulfate is a polyatomic with a 2- charge, and I only needed 1 copper. So that's why I'm saying you really have to memorize your polyatomics. And you really have to memorize the charges associated with those distinct columns. Memorization game, A point. You got to get that game on, okay? So what about an anhydrous salt? An anhydrous salt is a ionic lattice with no water. You guys have, again, already encountered it in an FRQ. An anhydrous salt is something that's been boiled the water off, so you have nothing but pure salt left, okay? Now, here's something that you should know about. Please be mature about this word. Cleavage, okay? So when we have ionic structures, they're in this like tic-tac-toe, right? Positive, negative, positive, negative. They create this like very structured nature. 1 column, row, column, row. If you apply a blunt force to it, you can create a cleavage, okay? And cleavage is simply separation. Sorry, Maggie's face is making me immature. Separation that is the result of a sudden force. Everything that's wrong in this class is Maggie. Separation that is a sudden force to the lattice structure. And what happens is when this occurs, you actually get the breaking apart, right? You get the breaking apart of the lattice structure, okay? And I realize that is illegible, so I'll rewrite that. The breaking apart, okay? And what happens is now you have loose ions because now you just have no longer bonded together. Now they're just like kind of floating. And remember, ions can technically float alone because they made the transaction. They're technically stable alone. Like you could technically separate an ionic bond. It doesn't love it, but you could, okay? And so what you do is you're now able to conduct electricity. Okay, in what we call an aqueous environment, in a water environment. So let's say you create a blunt force, such as blunt enough is stirring your salt cube. Okay, that's a blunt enough force. Hit the cube, it starts to break apart. You created a cleavage. Okay, the cleavage releases all the ions. Okay, now what you notice is if you put an electrical current through your water solution of salt, it would create a charge. You would actually measure electricity flowing. But if you just preserve that salt cube, okay, and you just left it in there, no blunt force, no stirring, nothing would happen. You could put a charge in there, nothing would happen. Okay, so that's ionic compounds. That's the biggest, baddest one of them all. We're gonna move on to covalent. Okay, covalent characteristics. These occur through atoms sharing, okay, electrons, sharing electrons. So, generally speaking, your like curves, your little bonding curves tend to be particularly applied to molecular or covalent based bonds, molecular or covalent based molecules, because there's a sharing element. Okay, sharing, yes.
Does that mean what you said earlier? That if I put like a cube of salt in water and don't touch it, it won't dissolve?
Theoretically, it's not perfect because there's a lot more water molecules than the salt. So the water molecules will like bash against it and break it up.
Oh, okay.
But theoretically, yes. Yeah. Sam, could you get your head off the table? It's one of my pet peeves. Thank you. Sachin, sit up. So, sorry, if my back dies, so does yours. Okay, so we can categorize sharing as equal or unequal, which by the way, we all know to be true. Sharing can be equal or unequal, right? Like when you talk about your siblings, okay? You don't always share equally. When your mom makes you share, you share, right? You share that little bit, right? Especially when you're talking about like your favorite, I don't know, pizza place or whatever. Okay. So what we say is that polar covalent bonds, okay, have unequal sharing of electrons. So that means if there were 2 atoms and they're in a bond together, it means one of those atoms is hogging the electrons. you please never draw it actually like this, but this is a visual of how you can kind of see. In the bond, there are 2 electrons. That's a minimum amount of electrons that can be shared in a single bond. Okay. What would happen is you'd have a zone where you have a partially more negative region, and you'd have a zone with a partially more positive because the electrons are leaning to one of those atoms. Generally speaking, the atom that it's leaning toward is going to probably be the more electronegative atom, right? E/N is shorthand for electronegative. We would say it has not a full charge because a full charge requires the full transfer of an electron. We would say it has a partial charge. A partial charge is a little delta symbol. It's a little lowercase delta. It looks like an incomplete 8 minus. And we would say on this end that we have almost like a partial positive charge. And this would, of course, be the less electronegative, the one that's just not as good as attracting an electron to itself in a bond. Okay, we could also draw this with an arrow. We could say we have a more partial region, and as we head this direction, we have a more negative region. This is called a dipole arrow. A dipole is 2 poles, a separation of partial charges, like the north and the south. Dipole, partial positive, pole, region, partial negative, pole, region. If you have a dipole, you are polar. If you have a separation of charges, you are polar. Okay. If you have an unequal sharing of electrons, you are polar. If you have a significantly more electronegative atom compared to a bonded, less electronegative atom, you are polar. Okay. Now, of course, there's, the good little kids that do share equally. That's non-polar. Okay. This is equal sharing. Yeah, that's definitely not Maggie. Okay. This is equal sharing. By the way, for all the parents listening to this, it's fine. Maggie roasts me too. Okay. Equal sharing, equal sharing. So, all right, that's what we have, equal sharing of electrons. So you would never draw any of that for a polar or a non-polar molecule. All right. So there's actually a scale that we use to quantify polar and non-polar. And I think I'm going to end up introducing it later in your follow-up video. So I'm not going to go into it, but you're going to delve more into this later. So let's look at how let's look at some common molecular compounds, or there's a lot of ways we could say it. We could say common covalent molecules, common covalent compounds, common covalent molecular compounds. Essentially, compounds and molecules has this overlapping nature of more than 2 atoms bonded together. Generically speaking, innuendo-wise, molecule tends to represent covalently bonded, compound tends to represent ionically bonded, but we kind of just use them. But if you want to be really nuanced, you'd keep covalent and molecule together, and you'd keep ionic and compound together. Super nuanced, so not important. Sorry. So let's look at some of these molecules. You guys are already familiar with a couple of them. They're called diatomic molecules. I think I introduced this already. Okay, in Unit 1. Brinkelhoff. Okay, these molecules are 2 atoms of the same identity that are sharing electrons. There's no metal versus non-metal. It's itself with itself. Some other ones are, of course, your polyatomic ions. I already said they're a group of covalently bonded atoms that together carry a charge. Okay, so any polyatomic not in an ionic bond, okay, is covalent. So if I just wrote SO4 with a charge of 2 minus, that's a covalent compound. That's a covalent molecule. But the moment I write SO4 with a metal, a cation, now we treat it like an ion. Now we characterize it as an ionic, okay, portion. Right? I love watching kids walk by and forget that we can see them, and like kids little flirting, just like so funny. So there are many types of molecular bonds that can occur. And this is only true for molecular bonds, only true. We can have a single where you have 2 shared electrons. We can have a double where you have 4 shared electrons, and we can have a triple where you have 6 shared electrons between the 2 atoms. We have a little table summarizing it and a little visual. Now, line-wise, we call it single line, double line, and triple line. That's how we actually diagram it in Lewis structures, which will be tomorrow's lesson. Okay. Notice something. We have this thing called bond order. Bond order is a arbitrary value given to represent the relative strength and length of that bond. A single bond, lo and behold, is called a bond order of 1. A double bond is a bond order of 2, and a triple is a bond order of 3. Shocking. Yes, I know, folks. Welcome to the advanced levels of chem. Huzzah. Okay. Strength-wise, the less bonds you have, the weaker you are. Kind of like with friendships, right? The less you have to connect with someone, usually the weaker that friendship is. The more in common you have, right? Childhood friends. I only walked out with 2, so I don't really know that much. But the more, okay, strong you have, right? Lengthwise, single bonds tend to be longer, all else being equal. Now, if you have different sized atoms, okay, now you have to take that into consideration. But if you're saying like, let's just say I have 2 oxygens bonded together and I have single bond, double, and triple, well, that would mean all else being equal, my single bonded 2 oxygens would have a longer bond between them than my triple bonded 2 oxygens. Okay, that's the big idea. Stronger, bigger, fatter, better. Okay, actually not really bigger, but yes. Okay, so bond order. Okay, it's just an arbitrary, okay, number assigned, okay, to a bond. And it just helps us identify what we're working with, because you're going to learn about resonance structure tomorrow in the next lesson. And resonance structure changes what that bond order. Suddenly that bond order means something. Right now, it kind of doesn't mean that much to you. It will. Okay. So when we name covalent molecules, okay, now that we understand the types of covalent bonds that can occur, single, double, triple, and again, this only applies to covalent. You cannot have a single ionic bond and a double ionic bond. Like, it is just transfer. It's just one transfer. Gain, lose. Okay. When we name, we do a similar thing. We always put the more positive, but here we don't have a true positive. So what we say is we put the less electronegative atom first. Okay, and it's usually the central atom. This is usually what we call the central atom when we're looking at the structure of it. Okay, more positive, and then we add on the more negative. Again, not a true negative, because a true negative would have to have a full electron transfer, but it would be the more electronegative. Okay, and so these are what we call usually the terminal atoms. We call these usually the atoms on the outside edges, usually terminal. Okay. And that goes, and then of course we add the "ide." We turn into IDE. But so that sounds relatively familiar. It follows similar trends, but what we add on is now we don't have charges to figure out how many atoms are in that. Law of constant proportion. We don't know the constant proportion. We can't use charges to figure that out. So what do? We just straight up tell you. This is like the one time that we're really straightforward as chemists. We just straight up tell you. Okay, we use Greek prefixes to tell you exactly how many of one type of atom is present in a molecule. You straight up tell people in Greek. That's right, folks. You straight up, yeah. It's like when I give you instructions and I'm like, I just told you how to do it, and you look at me and you're like, that's all Greek to me. Ayo, that's it. Okay, that's like that. So we have mono, di. If any of you took geometry in like 5th grade, you'll be fine. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Yeah, like exact geometry, right? Or if like any of you have read like any type of like Latin literature or Greek mythology, okay? Like things like that. Any of you read Plato or any type of philosophy thing, right? You should be kind of familiar with this language. I don't know how much they talk about shapes. I don't know. So for example, let's look at this. By the way, of course, you are gonna also have to memorize this. Like that's a given. But you should be fine, right? Do a little bit of geometry review. And what we have is, what is the formula for nitrogen dioxide? Nitrogen with 2 oxygens. Oxygen in a bond, and there's 2 of them. Notice it is a prefix. It goes before the atom it's talking about. Ide is a suffix. Some of you would like to strangle me. I'd like to suffocate Miss Judy, right? I'd is a suffix. Okay. What is the, honestly though, this is not my fault. You should like go for the AP college boards. Like this is not my fault. Okay. What is the formula for xenon tetrachloride? Whoa, tetrachloride. Go ahead and try that one on your own. Also, some of you guys probably noticed that right away we have a noble gas. We have a noble gas. And that's weird because noble gases are supposed to be inert. Well, there's something really special about this noble gas. Some noble gases, okay, I'm hearing a lot of audio. Some noble gases have to fulfill a very unique role in a molecule where they can accept, they're the only ones able to accept that role. And I will tell you that later in Lewis structured discussion. But xenon is a common noble gas that is actually more reactive. It's not necessarily inert. It's not a perfect trend, it's a general trend. So what do we have for the name of xenon? Okay, tetrachloride, or what do we have for the formula? Oh my God, it's a miracle. Good job. How about the next one? Problem 3.
Oh my god, Ava, did you
N2O5. Ayo. Also, congratulations on your swim stuff. I saw a picture on Insta. Good job. So, sulfur hexafluoride. Sorry, I was reading too fast. SF6. Okay, carbon tetrachloride. 5? 4? 4. Okay. Here's something interesting. We actually have another example of a molecule covalently bonded that acts like an ion. These are acids. Acids are any compound that donates an H+ proton, which is a cation. Okay, this is another unique example, kind of like polyatomics, but for a different reason, where we see a theoretically covalent compound, non-metal plus non-metal, acts like an ionic. Okay, so this is kind of a unique one. We're gonna investigate acids and bases. Acids and bases, okay, deeply in the coming units. This is gonna be a huge topic of yours. So you just hold on. Save this, pin it for later. Put it in the little tack board of pinning it for later. There's a couple unique names that we don't have, that we don't follow the rules. Water. We literally just call water water. We do not call it dihydrogen oxide. I mean, you could, but it's kind of weird.
There's a scientific campaign to scare people by calling it that. Saying it's the most dangerous thing in the world.
And you know what? The fools would believe it. The fools would. Okay. Next one is hydrogen peroxide. Hydrogen peroxide. It's not dihydrogen dioxide. We just call it hydrogen peroxide. Okay. And I definitely did not think we were going to finish in time. So I stopped here and I made the post lecture starting now, where you guys start digging into polarity more specifically and how to calculate it, as well as metallic bonds. But it looks like we are 20-ish minutes away from class ending. So here's what we're going to do is I'm going to stop here. You are going to take either some time to look at your scores and not take your tests back because I need those. I haven't put them in the grade book yet. You're going to use this time to do that. Finish up your corrections, MCQ, show me your AP problem workbook completion, and or start watching the video for tonight. You have a video post lecture about 20 minutes and then 20 minutes of a problem that helps you work through some of this stuff. So best of luck. Good job, guys.